What's up, y'all? Professor Hurley here with another edition of Purple Bear Biology. On this channel we talk about anatomy and physiology, microbiology, and then biology of life. If you're new, be sure to hit the subscribe button so that you can continue to follow all of these really cool videos as I release them. In this video, what we're going to talk about is the integumentary system. I'm so excited, I've got the jitters. We're going to talk about the integumentary system, something that you've utilized your entire life. Your integumentary system includes your skin, your hair, and your nails. It also includes some glands, specifically exocrine glands, kind of like sweat glands that, well, produce sweat, and sebaceous glands that secrete an oily compound called sebum. Sebum traps moisture and provides protection from bacteria in something called an acid mantle, which to me sounds like it's awesomeness right out of a comic book. What we're going to cover in this video is the function of the integumentary system, layers of our skin, cellular structure and how it affects our skin's appearance, and bad things that can happen to the skin like burns and cancer. Let's start with the function and the layers.
If you think about your skin as the primary organ of the integumentary system, you could probably come up with most of the primary functions. Our skin is an amazing organ that serves as our first line of defense against infection, protection against abrasion and cuts, and it even traps moisture to prevent water loss from outside of the tissues. Our integumentary system also aids in the regulation of body temperature. The body can regulate blood flow to the surface of the skin to either conserve or liberate body heat. Sweat can absorb some of the heat directed to the skin and remove it as it evaporates away. Cool fact alert! Did you know that hair found around the body serves as a place to trap heat? Your body even has a little control over the hairs. Have you ever gotten cold and then felt goosebumps? Kind of strange that our hairs seem to develop a mind of their own for a second, isn't it? Goosebumps occur as the body tries to trap heat in the airspace between the hairs and the skin.
Your skin also plays a key role in perceiving your environment. Billions of neurons connect, aka innervate, the surface of your skin so that you can perceive pressure, pleasure, and pain.
No doubt you have noticed that some regions of your skin are more sensitive than others. This is associated with the number of nerve cells connected to the area. Areas with fewer nerve cells tend to be less sensitive to individual points of stimulation. In addition to those features, your skin is used to facilitate the synthesis of vitamin D. The way that this works is actually pretty cool. You can think of vitamin D synthesis like stages of preparing something, for example, like bread. The sun gets used to make chemicals in a plant. We can then process that into dough, and then bake it into bread. Vitamin D synthesis in your body starts by your skin absorbing ultraviolet light, and it then converts chemicals found in the tissues to a prerequisite needed later. The chemical then gets shipped off to the liver for further conversion. Then lastly gets shipped off to the kidneys for conversion into the final product of vitamin D. This kind of production line is not uncommon amongst many chemicals that we need throughout the body.
That's all kind of neat. Now that we have an idea of the different functions of our integumentary system, let's shift our focus to the structure of the primary organ, the skin.
The skin can be divided into three primary pieces. The epidermis is the most superficial layer and is what provides water retention and abrasion protection. Moving deeper, we would find the dermis that is responsible for housing the exocrine glands and hair roots. This is also the layer where your blood vessels can be found to provide nourishment to the bottom layer of your epidermis. The ridges that can be found at the top of this layer are referred to as dermal papillae and are responsible for anchoring the epidermis and are what cause you to have fingerprints. The layer below the dermis is called the hypodermis, sometimes called subcutaneous tissue. While this tissue technically is not part of the skin, it does contain a lot of fat cells that provide energy to the upper skin layers and serves as an anchor point for the dermis and the epidermis. There are some pretty cool applications here as well. You may have heard of giving a subcutaneous injection to a patient. Heck, you've probably all received one of these injections in your life. Vaccines, allergy shots, and medicine like insulin are all injected into this site because they are rich with blood vessels and have immune system cells there to help recognize pathogens. Did you know that the angle that a needle gets inserted will have a huge effect on which layer of the skin or underlying tissue is affected? Some tests, like the Mantoux test, also known as the PPD test that is used to screen for tuberculosis, are only accurate when placed in the correct skin layer. The top layer of the skin, or the epidermis, is actually quite complicated and cool. We can divide it into 5 primary layers. Starting deep and working up superficially, each layer is called a stratum, and we have the stratum basale, spinosum, granulosum, lucidum, and corneum. The stratum lucidum is only found in thick skin, like the palms of the hands or the soles of the feet. You may have noticed that there are a whole bunch of different types of cells dispersed throughout these layers. Each of these cells serves a particular function in this organ. The most abundant cells are called keratinocytes, and they make up most of what is skin. In addition to keratinocytes, embedded in the basal layer, we can find Merkel cells responsible for light touch sensation perception. And we've got some melanocytes that can produce melanin pigment that protects our cells from ultraviolet light. In the spinosum layer, we can find dendritic cells responsible for immune system protection. All layers superficial to the stratum spinosum are composed of keratinocytes only. A couple cool things about the epidermis. First, it's avascular, meaning that there's no blood flow directly to the cells. Because of this, the farther away cells get from the dermal layer, the fewer nutrients they have access to. On top of this, as we move superficially, the keratinocytes actually begin to die. This occurs for 2 primary reasons. First, the lack of nutrients from the basal layer. Second, because keratinocytes actually build a protective shell around themselves made of a protein called keratin. Fun fact, your hair and nails are also made of keratin. This protein is incredibly strong, but does not allow nutrients into the cell. Thus, as the keratin levels rise, the cell becomes cut off from new energy sources and dies. The top layers of the skin are composed of dead skin cells that break off and fall away. To replace these cells, new cells form at the basal layer and push the cells above them up and away. Where does all that skin go? Well, believe it or not, it actually is the primary component of dust. An average person will shed about 8 pounds of dead skin cells a year. That's a lot of skin. The constant renewal of skin cells is an amazing process, but where does the skin pigmentation come from? You may recall that a second ago I mentioned that melanocytes found in the basal layer produce melanin that gives our skin pigmentation. Not only does this give us variable skin tones, inconsistency in melanin production or melanocyte distribution can lead to beautiful features like freckles and moles.
Melanocytes are perceptive little boogers too. If you expose them to increased sunlight, they will produce more melanin to protect your cells. The increased melanin production produces the characteristic tan that people have whenever they expose their skin to the sun over time. Why does your tan go away, by the way? Well, if you think about it, if you remove the sun as a stimulus, the melanin production is reduced. And as stated earlier, the skin cells will eventually be replaced. Skin cells that have this increased melanin are shed, and the skin returns to its paler color. While we're on the topic of all these cells, let's discuss skin cancer. Recall from our conversation about the cell that cancer occurs when the cell replicates out of control. Skin cancer occurs when different cells throughout the epidermis malfunction in this way.
There are 3 primary types of skin cancers: basal cell carcinoma, squamous cell carcinoma, and then melanoma. Of the 3 types of cancers, the rarest and the most deadly is melanoma.
But why is it more dangerous than the other 2? Well, melanoma has a potential to spread to other tissues more rapidly. Part of this is just due to the structure and function of the melanocytes. They're already built to shed portions of themselves to get melanin into the keratinocytes. Rapid dissemination to other tissues makes melanoma much more challenging to treat compared to basal and squamous cell carcinomas that are more localized for a longer period of time. Your ability to identify melanoma could save your life or a patient's life. Because of this, there's a cool way to remember the characteristics of melanoma called the ABCDE rule of melanoma.
Visually screening for melanoma involves looking for asymmetrical skin blemishes with irregular borders and multiple shades. Newly formed blemishes that are large regions of discoloration, or any that continue to grow and evolve over time, should be considered prime suspects for melanoma.
Okay, let's move on to our last topic for this discussion. Skin damage in the form of burns.
Burns come in 3 degrees. First-degree burns result from damage only to the epidermis and exhibit a reddening of the skin with some sensitivity to touch. Second-degree burns extend the damage to the dermal layer. These often can cause blisters and bleeding depending on the extent of the damage. If you have ever had a really bad sunburn that blistered, you've had a second-degree burn. Third-degree burns damage all the way down to the hypodermis and sometimes the underlying tissues. Interestingly, second-degree burns are actually more painful than third-degree burns because in third-degree burns, the nerve cells can be damaged, resulting in a loss of sensation to that region of the skin.
Burns themselves can create multiple complications that can be life-threatening. Some of these include rapid fluid loss and dehydration as moisture evaporates away. Additionally, infections from opportunistic pathogens can occur. When a patient enters a clinic with third-degree burns, one of the first things that must be done is to quantify the extent of the damage. More areas burned results in a greater likelihood of complications and reduces the chance that a patient can survive. Because of this, oftentimes a system called the rule of nines is used to assess patient condition with third-degree burns.
The rule of nines calculates the total body surface area that has been damaged and serves as a predictive value for patient survival. Here's how it works. The patient's body is divided up into different body regions that account for approximate percentages of the body. As a side note, the rule of nines is modified when considering children because their body proportions are different than an adult. And oftentimes the rule of nines is also modified if the patient has experienced smoke inhalation. Smoke inhalation into the lungs would reduce the likelihood of survival. So that's all well and good, but let's try an example. For this example of the rule of 9, we're not going to consider smoke inhalation, and we're going to use this simple equation. Scores are essentially an estimation of the likelihood of survival for a patient. The way to calculate the score is to take the total body surface area burned with third-degree burns and then add the patient's age. Now, if you get a value that's 140 or above, it's highly unlikely that the patient will survive. Oftentimes, students are like, oh my God, 140, that seems so low. But let's do an example so that you can see exactly what a score would be and how much surface area can get burned before you would get to a score of 140. So I want you to imagine that while roasting marshmallows around a fire, your crazy friend that you considered not even inviting in the first place decides to fuel the fire and dump gasoline on the flames. Before you can say anything, the flames roar up and burn your friend standing too close. Before you can put out the flames, they have experienced several third-degree burns, including on the anterior side of their cephalic region, the anterior side of their thoracic and abdominal region, and both of their lower limbs. They also received severe burns to both sides of both of their upper limbs. You rush them to the hospital, but because of your experience in A&P, you are mentally calculating their likelihood of survival. Now let's go through that calculation together. I have organized the different regions of the body that have received burns in this patient. Your friend has burns on the anterior side of his head, the cephalic region, and this accounts for 4.5%. They also have burns on their thoracic and abdominal regions, which would account for 9% each. And lastly, they have burns on both sides of their upper limbs, so this would account for 9% per limb, and they have burns on the anterior side of their lower limbs. They account for 9% each. If we add all of this up, we get a value of 58.5. This would be the percent body surface area that is actually burned. If your friend was 22 years old, we would add this to this 58.5%. 22 added to the 58.5 would give us a score of 80.5. Now I want you to take a look at your friend. Your friend has been burned severely on almost every region on the anterior side of their body, but yet with proper medical care, they would likely survive. So you now may be wondering, how in the world would somebody get a score of 140 or greater? Well, obviously burns over the entire body or individuals that are older. As you increase the age, the score will start to increase as well, and they can sustain fewer major burn sites.
Holy cow, that's all fascinating, right? I hope that you found this video useful. If you enjoyed it and found it helpful, then make sure you click the like and subscribe button so we can continue to explore concepts together. If you have any questions or want me to explore any of these concepts in more detail, then drop me a comment in the comment section below so I can continue to make content that you are interested in. Well, that's it for this episode of Purple Bear Biology. It was great to get to talk with you again, and I hope to see you next time.